So this homework assignment is all about potential energy, two forms of potential energy. Gravitational potential energy, which is mgh, the mass multiplied by the acceleration due to gravity multiplied by the height of an object relative to a chosen zero. And the spring potential energy, 1/2 kx squared. K, the stiffness constant of the spring, and x, its stretch from its equilibrium position. So here we are, problem one. The lowest point in Death Valley is 85 meters below sea level. Now, below sea level, I'm immediately thinking of that as a negative height. The summit of nearby Mount Whitney has an elevation of 4,420 meters. What is the change in the potential energy of an energetic, they'd have to be, 65 kilogram hiker who makes it from the floor of Death Valley to the top of Mount Whitney? Well, here's my drawing of this scenario. The dotted line is supposed to be sea level. It's not terribly level, but that's sea level, which means the height down to the floor of Death Valley is actually below sea level. And so that we should think of as a negative height. Now, it's my practice when solving problems involving gravitational potential energy not to choose negative heights. I always like to solve a problem by selecting the lowest point to be equal to zero. But this problem is forcing me to do it this way, so that's the way that it goes. The change in gravitational potential energy is the final gravitational potential energy here at the top of the mountain, minus the initial gravitational potential energy, which is here below sea level. So it's a positive gravitational potential energy, mgh2, minus a negative gravitational potential energy, mgh1. So I'm actually going to be subtracting potential energies to get the change in potential energy, but it ends up being addition. The way that I think about this, though, is the change in gravitational potential energy. I'll reset my zero to be down here, because that's the way I like to do. So this is zero. So how high does the person go? h1 plus h2. And I'll calculate the gravitational potential energy that way. It's not surprising that where you choose the coordinate system doesn't actually affect the answer, because that's the way it should be. Our physics should be independent of the coordinate system. But I calculate this as mg multiplied by the total vertical distance. The next problem on the assignment, let's see if I can click to it. Question number 2. We have a car traveling at speed, and of course that car has some kinetic energy. We want to calculate what is that kinetic energy in joules, and then we're asked from what height would we have to drop a car to have the same amount of kinetic energy just before impact. Well, here's the situation. I have a car going along the road with some velocity. So to calculate the kinetic energy, it's simple. 1/2 mv squared. I'm given all the numbers, so I'm going to get a certain number of joules. To find out how high I would have to drop the car from, I'm going to take this number of joules and set it equal to mgh, solve for h. That would be the height from which the car would have the same gravitational potential energy as the kinetic energy that it has going along the road. Also, it's not a coincidence that when I dropped the car from that height, when it reached the ground, it would be going the same speed as it had been traveling in the first part. The last part of the question asks about whether the problem depends on mass. And you might think that it does, because in order to calculate the kinetic energy, you need the mass in the equation, 1/2 mv squared. And then to calculate the height, you have to divide by that mass. It turns out the calculation really is mass independent, because when I compare the kinetic energy, 1/2 mv squared, to the gravitational potential energy, mgh, the m's cancel. And so the solution of the problem really has nothing to do with mass at all, despite the fact that the mass is given. It's a common thing in conservation of energy problems, and sometimes students start a problem, they say, well, I can't solve it because I don't have the mass. Very often you have to follow through with the problem in order to discover that the mass was not really necessary in solving the problem. Question 3 of the assignment. World's fastest humans can reach speeds of about 11 meters per second. Notice they did not give me the mass of the person. In order to increase the gravitational potential energy by an amount equal to its kinetic energy at full speed, how high would a sprinter need to climb? Interestingly enough, I'm surprised I didn't phrase it this way. It's sort of, if a person can generate this much kinetic energy, how high can they jump? In here it says climbing, but it might as well say jumping. So all I'm doing is just like I did with the car, comparing the running speed and therefore the running kinetic energy to the gravitational potential energy. 1/2 mv squared is equal to mgh. I noted that they didn't give me the mass of the runner, but that's okay because that mass appears on both sides of the equation and therefore cancels out, dividing through by the mass. All I need to do then is solve for h, the height to which that person would need to climb in order to reach that, or in order to have the same gravitational potential energy as the kinetic energy that they once had. Number 4, a 72 kilogram bike climbs a 1,500 meter long section of road at a slope of 4.3 degrees. How much does the gravitational potential energy change during this climb? Well, the thing is, it's on an incline. So here I've drawn my little incline plane. Here's the bicycle about to ascend at an angle theta. Now, the important thing to realize here is that they've given you the distance d that the bicycle travels up the incline. You want to calculate the gravitational potential energy, but the gravitational potential energy is not mgh, or I'm sorry, it's not, pardon me, it's not mgd, it's mgh, the vertical height that the bicycle goes to as it goes from the bottom to the top. So if I draw this triangle, I realize that the height that the cyclist ascends to is related to the distance by trigonometry. Being the opposite side of the triangle, it's equal to d times the sine of theta. If I assume that the lowest point is equal to 0, then the change in gravitational potential energy is simply equal to the gravitational potential energy the cyclist obtains, which is mgh. On to the next. Okay, how far must you stretch a spring with a spring constant of 1,900 newtons per meter to store 300 joules of energy? So here they're calling delta S the stretch of the spring. We would just call that X the stretch of our spring in the way that I've done the algebra in the lecture. Here is an immovable barrier with a spring attached, and I tried to imagine I attached a handle to it, and so I drew the handle backwards. Let's just imagine that that's a handle. It's ridiculous. I exert a force and I stretch the thing, a certain stretch, to get a certain amount of energy. Well, all I have to do is use the equation for the spring energy. The energy stored in a spring is 1/2 the spring constant multiplied by the stretch squared. A little bit of algebraic jiggery-pokery, and this equation becomes twice the spring energy divided by k square root is going to be the stretch of the spring in meters. Remember, everything meters, kilograms, and seconds when we're doing physics, and that problem works out easily enough. As does the last question on the assignment, which I think is going to be the same thing. How much energy can be stored in a spring, 500 newtons per meter, if the maximum stretch is 20 centimeters? Now beware, that says 20 centimeters. I should use that as 0.2 meters in any calculations that I do. And the calculation is very much the same one that we just did. The spring potential energy is 1/2 k, which they give me, x, which they give me squared. So this is a straightforward calculation giving me the spring potential energy measured in joules.